So again, I'd like to thank the organizers for giving me the opportunity to talk also in the discussion meeting and for their hospitality this week. Fantastic, I really enjoyed it. This is the 6th lecture that I've given in 7 days, and for the previous 5, I managed to spend the evening typing up slides, and then what with the trip, and so I'm gonna write on the blackboard, but I warn you that my institution no longer has blackboards, so it's many years since I've written on a blackboard. I hope it works. Okay, so what I want to do is something very simple-minded. I want to simply define a group. Arising from n normal subgroups in some group G. Well, I want to define it and I want to give some motivation for why it may be interesting. I'm actually going to focus on the case of 2 and 3 normal subgroups, but everything I say will work for n. So the focus the construction that I want to talk about, I'm afraid, is not at all new. It was in my very first paper that I ever published, so this is very old material. But for n equal to 2, the construction is known as the non-abelian tensor square and has attracted quite a bit of interest. I looked at there's a web page that keeps track of everything that's written on the non-abelian tensor square, and yesterday there were over 150 papers written on the case n equals 2, but practically no papers except for myself written on the case n equals 3 or higher, so I'm just shamelessly advertising a construction that maybe somebody will. Okay, so let me start with some remarks. Firstly, the construction I want to be, it doesn't matter on the order of the subgroups. You should get an isomorphism if you permute them. And the second thing is that for t equal to 2, for n equal to 2, this construction, which I'll just say, let's call the subgroups M and N rather than N1 and N2, that's just the non-abelian tensor square of 2 groups. So I want to say a word about the case n equals 2. That's the non-abelian or non-abelian tensor product. So this product first was defined in a paper of Ronnie Brown and Jean-Louis Laudet. Appeared in Topology back in something like 1987, 88. But it actually, the definition, I'll recall it, certainly derived from an old paper of Claire Miller, who was in the 1950s, wrote a paper on the second homology of a group. It certainly derived inspiration from work of Keith Dennis, who was looking for higher kind of K functors in algebraic K theory. And one name that never gets mentioned when this definition is written down is Philip Higgins, who unfortunately died last year. But I was a PhD student when the definition for n equal to 2 was being developed. It kind of arose over a few months. One summer, Philip Higgins was visiting the university where I was studying. And originally, the definition had 4 axioms. And on 2 occasions, Philip Higgins reformulated the axioms and knocked them down to 2 very simple ones, which when you see them, you wonder why all the fuss. So let me define then the non-abelian tensor product. It has generators. It's a presented group. It has generators, symbols, M tensor n for M in the normal subgroup M and N in N, and two relations which are commutator relations. So somewhere I should just say that I use the notation x, y conjugated by x, I write this way around, and my commutators I write this way around. So the relations for this group are simply that if you take a product, think of this as a commutator, M prime commute n, then that's the same as the commutator M prime acted on by M, N acted on by M, times M tensor N, and a similar one. Okay, so that's the group for t equal to for n equal to 2. It was actually this group that got me interested in computers. Ronnie Brown, Dave Johnson, and Edmund Robertson wrote a paper where they calculated this group for all of the groups up to and including the order 32. They did it by hand, and a couple of years later, I just thought, wouldn't it be great to try to do this on a computer? And that's what got me into GAP. I was so pleased because I could reproduce their whole paper in just about 5 minutes of GAP computing. My supervisor was not too happy, but Bettina Eich, a few years later, can do it in about 2 seconds. So my supervisor is even less happy. But anyway, so that's what got me into computing. And maybe I'll just mention, how would you go about computing this? So with this presentation, the number of generators is the order of m times the order of n. So if m is infinite, there's a problem straight away. And even if n is m and n are finite. So one thing you can do is you can take your two groups and take their free product, and then consider the inclusions, which I'll call I and j, and divide out by the relations. I don't know how to write this. So let me say, I take m, n, m. M is in this copy, n is in that copy, and set it equal to the element n acted on by m, where the action is in G. So this element lies in this copy. And likewise, and when you look at this construction, it turns out then that if you take so these are no longer injective, but if you take the image of m and the image of n, and look at the commutator subgroup in this quotient of the free product, what you find is that you get the tensor product. So for computational purposes, this is certainly one approach to computing, because the number of generators here is just the union, the number of generators of m and n, and the number of relators can be reduced as well. Do I need conjugation? Oh, sorry, I think I do. Thank you. That wouldn't make sense. Thanks. So there are some structural properties which are not too difficult to work out. Well, some actually are more difficult. If you look outside on the posters, there's a very nice poster by Anthony and Thomas, which has a nice structure theorem for the tensor square outside. But let me write down some properties for the tensor square. So this is for my construction and then nothing has been written, but it would be hard to imagine that it's not true. So for n greater than or equal to 3, I guess what I'm saying is a conjecture, because I haven't actually, nobody's ever written down the proof. Maybe I'll call my construction something. Let me call it Tn. So some things that are not too difficult to establish are that if G is finite, then the tensor product for T2 is finite. And I imagine one should be able to prove it for n greater than or equal to 3. If G is a P group, then this is certainly true for n equal to 2. And nilpotent. So I think one reason why the construction has found kind of applications is that there is a relation between the construction and homology groups. So let's just define, let me define the exterior product to be the tensor product divided by, let's say, subgroup generated by X, tensor X, for all X in M and N. And then you find there's an exact sequence involving, so if you take your normal subgroup N in G, and if you look at the third homology of G, there's a natural map to the third homology of the quotient, and then there's a map to the kernel of this, the map from the wedge product down to G, which sends a generator to the commutator. And that continues to second homology, integral homology, and so on. So what it does for you really is, this construction is all about commutators. It's a way of bringing into, everybody knows about Hopf's formula for the second homology of a group, it's all about commutators, but it's a way of using information on the third homology, kind of relating it to Schur multipliers and so on. It's just it's a nice kind of intermediate group. And there are two posters again. I forget the last names. Let's have a look. Outside, Rai and Hatri, both are based on this sequence. You know, for one is for classifying P groups with a certain property, and the other, well, they're both for classifying P groups. Okay, so what else do I want to say? The other remark I want to say is that, well, I was supposed to be numbering these. Final remark. When we look at the definition of the tensor square, or the tensor product, there are these two commutator relations, but there's no sign of the whole width identity. And when you look at any book on combinatorial group theory, the whole width commutator identity plays a role, and that's missing here. But for the construction Tn, for n greater than or equal to 3, we have to invoke the whole width identity. Okay, so those are the remarks. So I think before I give the definition will come at the end of the talk. I'll give some applications. So for 5 lectures, I've been talking about computers and getting out numbers. I now feel free to give applications which are very far from anything to do with computing. They're more kind of, You won't get numbers out of these applications so much, but let's have a look. So, first application. Maybe I'll number the applications. So let's just recall that for a group G presented as a quotient of a free group, we have Hopf's formula that the second homology is given by this formula. So I remember as a student wondering, I wonder what the formula is for higher homology groups. Is there a group theoretic formula? And using ideas from algebraic K-theory and free simplicial groups and so on, one can derive a formula for higher homology groups, analogous to that. And having kind of discovered the formula, it was then not too difficult to see that in fact one can reprove the formula using this group. So what's the formula for, let's say, H3? So this is a theorem, Ronnie Brown, and it says this: if you have a group G, which is a quotient of a free group F, the product of two normal subgroups, where F and the two quotients are free, then we find that the third homology of G is given by not a computational formula, but it looks rather nice. Well, it can be used to do computations in some simple cases, but second application of the tensor product, which is due to Ronnie Brown and Jean-Louis Laudet, involves classifying spaces of groups. So let's suppose then that we've got, for any group G, let's take the classifying space, which is the quotient of a intractable space with a free G action divided by the action of G. Given that, we can define the suspension of the space. So what's the suspension? You take your space, BG, and then you take a direct product with the unit interval and squeeze the top point, so it looks like this. So if my group G was the infinite cyclic group, the classifying space would be a circle and the suspension would be a two-sphere. Then there's a theorem, Brown and Laudet, say BL, which says that the third homology of the suspension of this classifying space is just the kernel of the commutator map from the tensor square down to G. And in fact, you can suspend any space, so you could even suspend the suspended space. And here you find that it's a kernel from a quotient of the tensor square. What you quotient out by is the tensors x tensor y times y tensor x. So there are some kind of applications. And in fact, the proof of this actually uses, so the proof of this just uses T2. The proof of this actually uses T3, and the fact that T3, which I have yet to define, also T of G, 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 when I define it, we'll find that T of G, G, G is actually this group. So just a quotient. Let me talk briefly about some work with Roman Mikhailov. So this is application 3. So let's just remind ourselves then that a presentation of a group let's say n relators is a spherical if the two-dimensional complex associated to the presentation has trivial second homotopy group. So let's define a presentation to be almost this spherical. If the presentation, which I'll define now, is a spherical, for all proper subsets of the relators. Okay, so that's the notion of an almost aspherical presentation. Oh, let me give an example then. If you take the 4-string braid group, and it's an example of an Artin group or the 4-string braid group, that is almost aspherical, but it's actually not aspherical because there's a sphere in it. So one application, I'll call it a theorem. It's more intriguing rather than useful. So let me define for my presentation, let F be the free group on the generators, and let me say capital Ri is the normal closure of the relator Ri. And then if you have a presentation P is almost aspherical, then let me look at my notes so that I get it correct. One's often kind of interested in working in free groups or quotients of free groups that are awkward. So let's take the product for all partitions of the set 1 to n of the following commutator subgroup. I'm going to take the intersection all the Ri's, the intersection of all the Rj's, take the quotient, and I'm going to look at that. Now, why you would want to look at that, I'm not sure, but it's a difficult thing to look at. And one thing that you can say is that, for example, this has no p torsion. Get it correct. For primes p greater than 2n. So why I think it's intriguing, I don't know that it's useful, but it seems to be intriguing in that how do we get this? Well, we take a classical result of Serre on the homotopy groups of spheres where information is known about p torsion, and then you transfer that back to combinatorial group theory. So it gives an approach, a possible approach to studying things in combinatorial group theory. Let me give another such application. So let's now suppose that, maybe I should call these propositions rather than theorems. Let's suppose that we have a presentation on n generators and n plus 1 relators. Let that be a presentation. Let it be an almost spherical presentation. Of which group? Of the trivial group. Okay, so take an almost spherical presentation of the trivial group. Then, again, so that I get the formulae correct, one can find that the n plus first homotopy group of the two-sphere, which is an object of interest, can be described by, again, an intriguing formula, the intersection of these Ri's divided by the same thing here. So one thing that follows from this is another formula due to G Wu, which I'll mention. Let's consider the following presentation. Take n generators and take the following n plus 1 relators. So every generator is trivial and the product. Then that's an almost spherical presentation of the trivial group, and if you plug that presentation into here, you get G Wu's formula for the n plus first homotopy group of the two C. So I won't write down the formula, but okay. So one fourth example, and then I will go on to the definition. Let me do this next example just for 3 subgroups. So let's suppose that we have 3 subgroups of our group G. And then let me do some constructions. Let me take the quotient homomorphism. Let me build a classifying space for both of those groups. There's an induced map. And by using map-in cylinders, we can assume that this map is actually an inclusion. And I can build a nice diagram. So maybe my M is here. So I have almost a cube of group or spaces. So let me now do the following. These are all inclusions, they're cofibers. So I'm going to take the homotopy co-limit, which really just means the union. So I'm going to take the union of all these spaces, call it X. then what one finds is that the fourth homotopy group of this space is actually the kernel of the map, commutator map. Well, I haven't defined this yet, so okay, I'm going ahead. I have to define what I mean by this. G pi 3 of x is the co-kernel of this map. So the quotient, well, actually, let me take the map just to, it's the co-kernel of, if I take L intersect N intersect N, and then just for completeness, pi 2 of x, if you're interested in it, is this intersection and by Van Kampen's theorem, which is in the title, Van Kampen's theorem for the fundamental group says that the fundamental group function preserves certain co-limits. So this is a certain, this is one that it preserves. So by Van Kampen's theorem, we would know that the fundamental group is G over the product L. X is the, so I started with my group and the three normal subgroups. I built all but the last corner of this space of inclusion, this cube of inclusions. And then I took X equals the co-limit of the diagram, which to me means the union of all these classes. So if I take all of those classifying spaces and I take their union, that's my X. Okay, so I'd better define the group that I was talking about, so let me do that. So to define it, let's introduce some notation. So let me write the following: A1, this joint union A2, or whatever. Let me write this. Suppose I have a number of sets, A1 to AK, and I'll write that equal to N to mean that the union of the A's, K sets, is equal to 1 up to N, that they're pairwise disjoint. Oh, and that none of them are empty. Okay, so I'll use that notation to mean these three conditions. And I'll also say that for when I've got n subgroups, I'll define n subscript A just to mean the intersection those ni for I in A. Now I can come to the definition. So the group that I want to advertise has generators, the symbols, let's say A tensor, and I'll use the following notation, A comma B, B, for all pairs of sets partition N with A in NA and B in NB. And what are the relations? Fortunately, I came in when the photo was on. The relations are 1 to 5. over there. And in preparing this talk, if anybody is interested in looking at this group, in the original paper, everything is fine, but in the paper with Roman, it's my fault because I did this. I actually forgot to include relation 5. So just be careful if you do get excited about this. Remember that relation 5, for some reason, is a typo. It isn't included in the latest paper. Okay, so I have a few minutes left. So where does this definition come from? It's maybe something I can say. Our original motivation for the definition is that Barrett and Whitehead back in the 50s calculated the first non-vanishing homotopy group of an n-tuple of spaces. But they had certain abelian conditions, and we wanted to extend that result in a non-abelian setting. And so that was the original motivation for the paper back in 1987. I should actually say that Tn appeared in print before T2. But anyway, but where does the definition come from? Well, let me just talk about the Brown-Lode approach to Van Kampen theorems. Van Kampen theorems. So what they establish with Richard Steiner as well in Glasgow is that there is a functor which I'll call capital Pi, which goes from the category of n cubical diagram, n cubes of spaces. This is a 3 cube of spaces. It goes from n cubes of spaces and it ends up in algebra. And the algebraic category is the category of groups endowed with n compatible category structures. So groups and the important thing about the functor is that it preserves certain, I won't go into the details, it preserves certain colimits. So for n equal to 0, a group endowed with 0 compatible category structures is a group. And a 0 cube is just a space, and pi is just the fundamental group. So for n equal to 0, what I've written as capital Pi is just the fundamental group. And Van Kampen's classical theorem says that the fundamental group of a union or a colimit of spaces is equal to the colimit in the category of groups. So there you have to talk about amalgamated products in groups. So in order to apply Van Kampen's theorem, you have to understand the category of groups and explicitly construct colimits. So to apply this, what you really need, well, there are two aspects. One, there's the topological side, but the algebraic side I'll focus on. You have to construct colimits in this category. And so let me just give a nice formulation due to Jean-Louis Naudet of this category. These objects, I'm actually going to call them cat n groups. When these were being named, the original name was n-fold category. And there was at a meeting where Saunders MacLean was in the audience, and Jean-Louis Laudet was talking about this, and he talked about his n-fold categories, and MacLean stood up and said, you cannot use that word. And he insisted that Laudet wouldn't use the word, so it was changed to cat-n groups. So let me explain what a cat-n group is. A cat-n group is a group G with endomorphisms which I'll call S for source and T for target from G to G. So I'm thinking of G as being a category, and S takes an arrow. I mean, it's a group, but in addition, I'm going to think of every element as being a category. S is the source of an arrow, T is the target. But I have n of these structures. And then what are the conditions to capture the fact that you've got category structures? Well, firstly, we want S goes to the source of, so I think of the source of an arrow as being the identity. So the source of the source is just the source. And the target of an arrow, I think of it not being an object, I think of it as being the identity on that object. So the target of the target is just the target. A category structure is a partial composition. So it means that for certain pairs of elements, I have to be able to compose them, and that composition has to satisfy the axioms of a category. And it gets kind of messy, but Laudet rather cleverly formulated it purely group theoretically as follows. All you need is that the required category structure can be defined provided if and only if the following holds. If you take the kernel of the endomorphism Si and the kernel of the endomorphism Ti, they actually have to commute. And then the third condition is that these category structures have to be compatible. So you need that Si, Tj, they commute. And so where does this definition come from? It comes from looking at the functor pi. You end up in an algebraic, with algebraic objects, which are cat-n groups, and then you want to construct the co-limit of those cat-n groups, so you have to analyze the algebra, and out pops, as part of that structure, this group here, what I'm calling Tn, and given that T2 has generated over 150 papers, maybe after this talk, T3 might attract some interest. But I have 1 minute, 52 seconds. I think I'll stop early today. Thank you. So, they're not so much third homology, but they, you want to if you're interested in homology of groups, really, for any group G with a normal subgroup, you have this map, and then you have something goes in the middle, and it's a long sequence. So what I put here was the something involving the exterior product, but I think really you should call this Hn of G relative to n. Okay? And that's using the tensor T2. Now, that is handy in looking at, say, the Schur multiplier or something. But you could say, well, I'm interested in this. So then you take two subgroups, M and N, and I suppose you can do something like this. And then there'd have to be something in you know, and then you go down to hn minus 1, gn. So you'd have to put something here. What would you put there? You'd put what we might call a doubly relative homology group. And how would you access that? Well, it would be an exterior product, but a threefold product. So I don't know if that answers the question, but I mean, if you want to get at homology or use this for homology, it's kind of doing that trick twice. For a pair of groups, I have to be careful because I'm a bit out of touch. I don't think anybody has written one down, so I don't. But you can in-gap compute these things because it's all programmed. You can also do this at the level of chain complexes and so on. So these relative groups you can actually, for finite G and so on, a polycyclic G, you can calculate the relative groups.